Good morning, everyone. So we will be covering tutorial 6 today, and if possible, I'll also try and finish up the vectors. So hence, tutorial 6 is on your multivariable functions and partial derivatives, which will be tested during your quiz 2 next week. So for question 1, do you have any requests on any of the parts? Yes? Sorry? D? Okay. Alright, so for 1D, right, you have a function, multivariable function of two variables, x and y, defined to be y over x squared, right? Okay. So first of all, we are supposed to define the domain and range. So you can observe that, of course, this is y over x squared, and when x is 0, it will be undefined. Okay, but really y can be anything. It's just that x cannot be 0. Okay, so therefore we can write the domain down. So the domain is y is an element in R. That means y can be anything, right? And then x cannot be 0. Or you can also write it as x is an element in R, but given that x not equals to 0. Okay? So this is the domain. Yeah. You can also use interval notation if you want. Yeah, okay. So, yeah, you can also write it in interval notation, right? Yeah. No, as in you have to, the domain refers to the inputs, to the values of the inputs, such that you can calculate the output f. Right? So therefore, for y, you can also write it as minus infinity, comma infinity. If you want to use the interval notation, okay, then this will be, of course, comma, then your x, right? So your x cannot be 0. So your x is an element in this case, minus infinity to 0, union 0 to infinity. Just cannot be 0. Actually, it doesn't matter. As long as you cover the proper range. When I say range, I mean the interval for each variable such that f can be calculated, then it's totally fine. So that will be for the domain, and the range, right, will be, so what do you think is the range? So the range is just that, right, because you are dividing by x squared, so it cannot be 0, right? Because you can divide by a very large number, and then f is going to approach 0, but it's never going to be 0. Okay, but if y is 0, then x is a non-zero number, then certainly the function will return you 0. Okay, because you get, like, for example, f equals to 0 over 4, let's say. Right, you can get 0 as part of the range. Okay, but it's just that you cannot have, what did I say just now? Okay, so I contradicted myself. So in fact, you can get 0. Okay, because y, this y can be 0, it's not a constant, right? So therefore, the range is actually R. Is that alright? That means this x squared can be very small, right? So if x squared is small and y is a non-zero number, then f is going to go infinity. Okay, but y can also be a negative number, so therefore f can go minus infinity. Alright? Hold on, let me just save this. So then what about the level set? So the level set is when you have f equals to c, right? So therefore you have y over x squared equals to c. So the function f equals to y over x squared equals to some constant c. Okay, and of course this c must be within the range, right? Or else it doesn't make sense. The constant, whatever constant you want it to be, must be within the range, which is the output of f. Okay, so therefore this means that you have y equals to cx squared. So actually y equals to cx squared is a parabola. Okay, so parabola with the vertex at 0, 0. At the origin, because if you draw cx squared, then basically you're just getting either the smiley face or sad face. So if you like sketch it, right? So this is what you should get. So it depends on C, right? So you have something that looks like that. Okay, so this will be for C more than 0. All right, and then you can have this. For C less than 0. But if C is equals to 0, then you'll get the x-axis. So now I use different colors. Okay, so if it's C equals to 0, then really you get y equals to 0, right? So you therefore get the x-axis. Okay, so you can say that it is a parabola with vertex at 0, 0 for C that is not equals to 0. For C not equals to 0, right? So, and then you have y equals to 0 when C is 0, so which is just the x-axis. X-axis for C equals to 0. Is that right? So this will be a more complete description considering all cases for C. Okay, because your C here, as I mentioned, right, this C must be in the range, but the range is R ma. So that means C is an element of R. Is that right? So C can be anything. Can be more than 0, less than 0, or equals to 0. Any questions? F, sure. Any questions regarding this part D? Good? Yeah. No. The thing is, right, you have to consider the various values of C for which you can possibly get a different looking function of the level set, right? So, because level set very simple. Level set actually you just set the function to some constant C. Then this C must be within the range. So therefore, if you set this to C, you just multiply x squared across, you get a cx squared, right? So this is obviously a quadratic function, right? Which will give you a parabola. Then this parabola, obviously if C is not equals to 0, then you can get the parabola. But C can be 0, because C can be any real number. So therefore, if C is 0, then you get y equals to 0, which is really just the x-axis. So because the x-axis is a straight line and it looks different from the parabolic shape, right? So therefore, we describe it differently. That means you will have like two descriptions, right? But this is not the, what do you call that, the case for all functions. So 1f is describing this function denoted by sigma, right? There is a function of x, y, z. That means this is a function in three-dimensional space. Okay, so at every x, y, z position, you have some sigma output, okay, which is like, for example, a stress value, right? Because sigma are commonly used to denote stress in a material, for example. So it is defined by the logarithmic function here, right? Okay. So, but then because you have x squared plus y plus 2y squared plus 2z squared, which means that the argument for ln is actually more than or equals to 0. Correct or not? I mean, this itself, right, is more than or equals to 0. Okay, because when your x equals to 0, y equals to 0, z equals to 0, you can have 0. But you cannot ln 0. Correct or not? If you ln 0, then you undefined, because it's approaching minus infinity. So therefore, you have to exclude 0. Okay, you have to exclude 0. So therefore, right, we have to exclude the equality sign. Can okay? So therefore, let's exclude the equality sign, and then we can write down the domain already. Okay? So the domain is r cubed. Because now you have x, y, z, so r cubed. Given that, right, x, y, z cannot be 0, 0, 0. So that means it's r cubed, but excluding the origin. Because you plug in the origin, 0, 0, 0, then your ln is giving you undefined or minus infinity. So therefore, that's not a real number output. Okay, so that's the domain. All right. Then what about the range? Because your ln function, right, is looking like that. This ln function looks like that, right? Looks like that. So it's ln whatever this is, right? So for example, let's say ln W. Okay, and this is W. So ln W is like that. So therefore, if you have your W, which is this expression, okay, and this is clearly more than 0, which defines the domain, and then the range can see from here what? Which is R. Of course, can be anything. Is that right? So next will be the level set. So level set is when you set the function sigma, okay, equals to this ln expression, and you set it to be a constant, okay? So you set it to be a constant, you can e both sides, right? Exponentiate both sides, and therefore you get the argument equals to e to the c. Okay, so what happens is that this expression, okay, if you don't know how to describe this expression, it's okay. You just leave it as this, okay? Of course, you have to write like c is in the element, is an element of R. So c is an element of all real numbers because it must be within the range. Okay, so if you don't know how to describe this, it's okay. Actually, you can just leave it like that, right? But actually, there's a description for this. Okay, actually, this is the equation of an ellipse, but in 3 dimensions. Okay, so actually, this guy is equation of an ellipse in 3D. Okay, which is called an ellipsoid. This ellipse in 3D, which is an ellipsoid. Ellipsoid, I think this is the name. Is that right? Okay, so this is actually the something like an average radius squared, okay, of the ellipsoid. And if you plot this out, right, you can see, you can plot this out in Desmos 3D, and you can see that it looks like an egg lah. It looks like a Mentos or egg. Depends on how you want to scale the coefficients for the x square, y square, and z square term. Yes? Yeah. Actually, no need lah. I want to test you on the description, which I think is quite fair lah, because of course there are so many different kinds of like polyhedrons, as well as different kind of shapes, and then also solid objects, right? So it's not possible to know all the names. At least that's not our objective. Okay, so you can see that if you were to look at, it should be Desmos 3D. So you can have a look at the ellipsoid. So it's x squared plus 2y squared plus 2z squared, right? Then equals to some constant. So the constant doesn't matter. Okay, so I can just put equals to c, right? So you can see that if I increase c, right, then the size of the egg here becomes bigger. So this is what we call an ellipsoid. Okay, so if it's x squared, y squared, z squared here, right, no 2, then it will be a sphere. E to the c doesn't matter. E to the c is just another constant. So you can put e to the c, then it will be a super big. Is that right? So this c can be anything. So this is how the ellipsoid looks like. Then if you change, like for example, the coefficients, right, then you can change the so-called aspect ratio of the ellipsoid. Okay, so for example, if you put a 4 here, right, you can see that it squeezes the ellipsoid in the x direction. Can you see? Then it becomes like somewhat of a Mentos looking shape. Okay? Yeah, so this one, if you know, then you describe. If you don't know, that never mind, you can just leave it. Oh, why is it that if this is a 4, then it will squash the egg in the x direction, right? Because at y equals to 0 and z equals to 0, representing the x-axis, correct or not? So if let's say you have x equals to 0, if you have y and z both equals to 0, then you can solve 4x squared equals to some constant for x-intercept, for the x-intercept. So the story is, let's say you have kx squared. So you get kx squared equals to some constant, let's say c. So you can see that x squared equals to c over k, right? So x equals to plus minus root c over k. So you can see if k is large, then the x-intercept will be small. So therefore, there's a squashing effect if you multiply by a larger k. Okay, so this will be for 1F. Any other requests? Yes? Okay, so for question C, right, because you cannot root a negative number, right? So therefore the requirement is this argument must be more than or equal to 0. The root expression here, this rooted expression must be positive or 0. So then you just rearrange terms, then you get x squared plus y squared must be less than 16. As in, you don't, I don't think you can write it in any other way. The reason is because, right, you have to present this as a disk. This is a disk of radius 4. Agree? This is a disk of radius 4. So you cannot split up the x and y. That means you cannot say that x is like within some interval, y is within some other interval. You can't do that. Is that right? Okay. If you change to polar coordinates, right, you can simply say that the radius must be less than or equals to 4. Because this guy, x squared plus y squared, is actually r squared. This guy is r squared. So r squared is less than 16. So that means r must be less than or equals to 4. Okay? So it's actually a disk with the radius less than and equals to 4. If you change to polar coordinates. Okay? So yesterday we talked about polar coordinates. Because this x squared plus y squared is just r squared, right? Right? Okay, so not to confuse you. Right, so I think that's all with question 1, right? Okay, then the rest you DIY. So let's look at question 2. Okay, question 2, actually just differentiate. First and second order partial derivatives, but you also need to get the mixed partials. So do I need to go through anyone? D and E. Okay, so first and second order derivatives. So this one is e to the xt times ln xt, right? So first of all, let me write w sub x. So differentiate respect to x, right? So because you got two functions here, you got to use your product rule. Because two functions of x multiplied together, correct not? So therefore the first one, maybe I hold e to the xt, then differentiate ln xt with respect to x. So what do I get? I get 1 over xt. Then after that, I need to use what? Use my chain rule. So differentiate xt with respect to x, I will get t times t. Then plus, so now I hold the ln, then I differentiate e to the xt. But differentiating e to the xt, this t is a constant, so I chain rule it down. Then this will be ln xt put back. Is that right? So just using product rule. Okay, so of course you can simplify, and that looks like e to the xt. Then there's a 1 over x here, right? So you get 1 over x plus t ln xt. So this will be w sub x. Any objections? Then w sub t, actually you can see that the function is symmetrical in x and t. The function is symmetrical in x and t. So which means to say that if you swap x and t, right, actually the answer is still the same. Okay? So therefore what you can do here, right, is to just swap the x and t. So e to the xt is still e to the xt. Then this is 1 over x, then become 1 over t. Then plus, so this is t ln xt become x ln xt. So you don't even need to re-evaluate. Is that right? So this will be w sub t. Then what about the second derivative? So second derivative, you just differentiate w sub x with respect to x again. Let's say you get your w sub xx. Okay? So therefore this w sub t, maybe I move it one side first. Later then we come back to that. So then you just have w sub xx. Then you just differentiate this off. Okay? So e to the x, so of course you need to use your, what do you call that? Your product rule again. So for the first part, maybe I just e to the xt first. Then after that, I differentiate this thing. Differentiating this with respect to x, so I get minus 1 over x squared for the first term. Then after that, for this part, right, actually there's only one function of x. So it's really plus. So the t you put now is a constant. Then this guy, right, is going to give me 1 over xt. Then chain rule times t. Okay? So therefore, this is the first term. Now remember, I need to use my product rule. So therefore, now I differentiate e to the xt with respect to x. So t e x t. And I just put down the entire bracketed term. Is that alright? Okay, so you can simplify this because you have a e to the xt here. So therefore, it's e to the xt, then big bracket. So this is a minus 1 over x squared. I think that's the only 1 over x squared term. So minus 1 over x squared. Then this guy looks like what? 1 over t times t, right? So this is t over x. And then there's another t over x here. So it seems to be giving me 2t over x. Then after that, you have your final term, which is this t ln xt. Is that right? Oh, sorry, t squared, because I multiply the t in. Did I miss out anything? Correct, ah? Okay, then w sub tt then. So w sub tt. Okay, so w sub tt is differentiating w sub t one more time. Okay? So therefore, it is going to be, once again, symmetrical to this. So I'll just write down directly, e to the xt, because this one e to the xt ma. Then this is minus 1 over x squared, so become minus 1 over t squared. Then plus, so this is 2t over x, right? So become 2x over t. Then plus, then this is t squared, so become x squared. Then ln xt is ln xt. So you just make use of the symmetry here. Write down the answer. And finally, you have your w sub xt, your mixed partials. Okay, so for mixed partials, right, maybe you can get from w sub x. So now you get w sub xt, your mixed partials. So mixed partials means you differentiate w sub x, right, respect to t. So therefore, you will need to use your product rule. So e to the xt. Then this bracket, right, the first term is actually a function of x, so it's like a constant. So you differentiate 1 over x respect to t, get 0, right? So maybe let me write 0 plus. Then when you differentiate the second term, you got to use your product rule because it's two functions of t multiplied together. So therefore, you have t, I hold the t first, then multiply by 1 over xt times x. Okay, then plus. So now I differentiate the t, I get 1, then I just put back the ln xt. Okay? So then this is just the first term. Okay, because it's e to the xt times this, so I use a product rule here, but I'm using a product rule outside also. So therefore, I must plus, okay? So then I differentiate this respect to t, I get x e xt. Differentiate e to the xt respect to t now. Right, so the x is the constant, I bring down. Then certainly the second bracketed term, I just put back. Because I differentiated it earlier on already. So therefore, the net result, if you want to simplify, will look like e to the xt, big bracket. So this is giving me 1. Am I right? This is 1, right? So this looks like 1. Then there's another 1 here. So it's actually 2. Then you have your plus ln xt. Then you have plus xt ln xt. Is that correct? You can check against the answer given. Did I get it wrong? Did I mess up? Huh? This one? Is that okay? Okay, so finally the w sub tx, you should verify, but you'll get the same expression here. So therefore, you do w sub tx is also the same expression. It will be. Yes. Yes. As in, w sub tx by right is that you differentiate with respect to t first, then after you differentiate with respect to x. But then the expression you get in the end, right, will be the same as w sub xt. So unless the question specifically asks you to evaluate both, there is no need to. Just evaluate one, right? And then you just say that the other one is equivalent to the first one. Correct. And the mixed partials. Mixed partial also second derivative, because you differentiate twice. Can? Like that? It's quite long, so maybe, let me see. Maybe 10 to 12 marks. Because it's quite long. Okay, so that will be for question 2D. And you also want me to go through question 2E, is that correct? So question 2E, Obviously, this one just testing you on the fundamental theorem of calculus, right? So you integrate small g, you get big G, right? So after you get big G, you sub in the limits. So you can say that this is g of y minus g of x. Why not? Integrate small g, give you big G lah. Then after that, sub in limits. So certainly you get big G of y minus big G of x. So then, from here, right, you want h sub x. So this is actually quite easy. H sub x. So h sub x is obviously just differentiating this whole expression. So the first term is 0. 0 minus big G prime of x. But big G prime of x is obviously small g, what? Because integrate small g get big G, differentiate big G get small g, what? Fundamental theorem of calculus. So this has to be minus small g of x. That's it. Okay? Then you differentiate one more time. So h sub xx. Then h sub xx is just differentiating this, ma. So therefore it's just minus g prime of x. Is that alright? So then h sub y then. H sub y must be g prime y. Oh, sorry. Yeah, correct. So it must be g prime y minus 0. So this will be g of y. Then h sub y must be g prime of y. So then what about your h sub xy? 0. Because you differentiate minus g of x. So it's a function of x. The whole function of x differentiate respect to y gets 0. Okay? Which is obviously also h sub yx. Because you differentiate g of y with respect to x, you also get 0. So actually part E is just integrating the fundamental of calculus with your partial derivatives. Any objections? Any questions? Any part not clear? So you can see I can put g prime here, right? I put g prime because obviously the small g of t is a function, is a single variable function. So you integrate single variable function, you also get big G, which is a single variable function. So therefore, when you differentiate, you can put g prime. But when you have a multi-variable function, you cannot put g prime. You cannot put like prime, as I mentioned. You must put a sub x or sub y or sub whatever independent variable that the function is of. Okay? Okay, so this one done. The rest you DIY. So let's look at the next one. Okay, this question 3, I don't want to do because it's the same thing as what is being covered, what has been covered in lecture. So this one more of letting you mess around with GeoGebra or Desmos 3D, and then you can try and visualize the gradients, okay, in the respective directions. So this one for your own experiential learning. Okay, question 4, data analysis problem. Okay, so I'll go through with you probably. Or I don't need to go through, you can get the values yourself. Yeah, so we have this temperature that is in the aircon room, measured at various positions, x, y, z, in meters from a corner on the floor, given in the table. So I'm supposed to estimate the rate of change of temperature at the location 222 in each direction. Okay, so it's like in this room lah, right? Then you have one corner, maybe the corner at the door there. Okay, so that's your origin. So then of course you can have your x, y, z coordinate, okay, in the 3 perpendicular directions in R3. So therefore now, so they take a thermometer or thermocouple, right? Then after that they just, at every interval of 1 meters, they measure the temperature, okay, at some points. So therefore you're supposed to now estimate the rate of change. So first of all, we are supposed to be looking at the location 222. This 222. So you can see that 222 is here. This is 222. Okay, this 222 is this 222 x, y, z equals to 222. So at 222, the temperature is 25 degrees Celsius. Okay, so then we are supposed to estimate the change in the x and y and z directions. Understand? Okay, so of course, it depends on what step you take, right, in which direction. So in order to get t sub x, for example, t sub x, you need to step in the x direction, what? T sub x. So in order to step in the x direction, your x must change, but the y and z must keep constant. Okay, so for example, you are at 2, 2, 2 now. Then you take a step to 3, but you maintain the 2, 2 in the y and z directions. So isn't this you are taking in the x direction? Taking a step in the x direction, correct or not? So therefore you must maintain your y and z. Don't change that. So then you are going to get t sub x. So t sub x is approximated by change of t in the x direction divided by change of x. Okay? So this one must be in x direction. Okay, nah? Change of t in the x direction divided by the change of x. So therefore, what's the change of t in the x direction? 25 to 26. So this one is 26 minus 25. Can you see? 26 minus 25. Then divided by 3 minus 2. So therefore, the answer is 1 degree Celsius per meter. Any objections? If you understand that, then the t sub y and t sub z, right, will be trivial already. Okay, so you also do the same thing. Y you move. Then you keep x and z. So obviously you have to move to this y here. Then your x and z don't move. Okay, so therefore your t sub y then. T sub y must be approximately. So you look at the temperature is 25 at 232. So it's 25 minus 25. Because the original temperature at 222 is also 25. Then divided by 3 minus 2. Sorry, this will be t sub y. So therefore the answer is 0. So it's not changing in the y direction. Okay? So I think that's easy. Then the last one is that you move z. So you move z must be moving here. So z go to 3. And then you maintain the x equals to 2, y equals to 2. Okay, so t sub z will be approximated by change in t over change in z. So this guy will be equivalent to 23 minus 25. So you're going to get minus 2. Any questions? Smaller minus the bigger one. Because you must take the final temperature minus the initial temperature before you step. So after you step, then minus the one before you step. Is that okay? So this is really testing you on the understanding of the partial derivative, which means that you have to lock the rest of the directions, right? And only move in one direction. So that's the meaning of the partial derivative. Okay, so can you move in the diagonal, like, for example, a diagonal along two directions or not? Let's say, for example, you move from 2, 2, 2, right, to maybe say 3, 3, 2. Did I give? Let's say, for example, you move from 2, 2, 2 to 2, 3, 3. So 2, 3, 3, what does that mean? That means, right, you are moving diagonally in the y and z directions. Correct or not? So can move like that or not? Can. Okay, but the derivative, when you move in a so-called combined direction, right, it's not called a partial derivative. It is called a directional derivative because you are given some diagonal direction to move. Okay? So therefore, that will be covered in topic 7. Okay, it's called directional derivative. Okay, which is no big deal. Actually, you just take dot product, can you? Okay? Yes. Correct. Minus the initial. Always like that. Okay, so by the way, the calculation that I've illustrated is what we call forward difference. Forward difference because I step forward. For example, from x, right, I step from 2 to 3. So therefore, that's called a forward difference. I step forward. But I can also do backward. Backward difference means I must step from 1 to 2. I step from 1 to 2. I can also estimate what is the gradient at 2, 2, 2. That's called backward difference. Okay, then there's another school of thought that is called central difference. Central difference means, right, to find the gradient at 2, 2, 2, I must step from 1 over to 3. I can step from 1 to 3. Okay, so that means I like straddle over 2. So it's called central difference. Okay? Huh? So it's like that. Yeah, so let me illustrate. Okay, this thing I won't, I'll just show you, but I won't upload because I am worried that it will confuse some of you. So let's say this is your temperature function, right? That is in the x direction. So therefore, this is the point where x equals to 2. Okay, so it is x equals to 2. So it's your x. So now what we have showed you here is that I've taken the forward difference. So I take this temperature and this temperature. So I'm using this secant line to estimate the gradient of the tangent line. So let's say your tangent line, right, looks like that. This is your tangent line. So I'm using the blue line, the gradient of the blue line, to approximate the gradient of the tangent line, the orange line. Okay, so this is certainly one method. But this is what we call forward difference. But you can also use backward difference. What's backward difference? Backward difference is that you take a point here. So you are using this instead, the light blue. Okay, you are using this instead. Of course, backward difference and forward difference can give you different values. But I can also take central difference. So central difference is from here all the way to here. Okay, the green line. So I'm using the green line slope to approximate the orange line slope. So got all kinds of methods. Okay, but not important. You just take the forward difference. Can already. Okay, question 5 is on implicit differentiation applied to partial derivatives. Do I need to do question 5? Good. DIY. So you better practice. Okay. 6C. Yeah, so this one using chain rule. Okay. So requested for 6C. So we have a z that is a function of x, y. And then x and y are both functions of r and theta. So this is what? This is like your polar coordinates, right, that we have gone through yesterday. Okay. So nothing much, just trigonometry lah. X is the adjacent, y is the opposite. Yeah, then, obviously z is like trying to find some angle, for example, because you do tangent inverse, okay? So now, regardless, so we can find our z sub x. Oh, sorry, not z sub x. Okay, so because we have x, which is a function of r theta, y also a function of r theta, right? So eventually this z, if you sub in the composite functions, right, will be a function of r and theta. Is that right? Okay? So maybe we write it something like that lah. So just going to let, so this z, right, be z bar. So this z bar will be a function of r theta. Okay? Why I write z bar? Because z bar is not the same as z. Okay? Because z, right, is a function of x, y. So therefore, this guy will be what? Will be like x as a function of r theta, comma, y as a function of r theta. Can So I write z bar, which is the function of r theta, after you sub in the expression, okay? Because it probably wouldn't be giving you a tangent inverse function, or maybe it will give you a tangent inverse function, but it will not be exactly looking like that. It wouldn't be like, for example, tangent inverse r over theta. It won't be like that, So therefore, it wouldn't be the same function. So therefore, let me write it as z bar. Okay, z bar or z, doesn't matter whichever alphabet you use. So which means now I want to have z bar sub theta. So z bar sub theta means you have to differentiate. So del theta. Okay, differentiate theta, differentiate respect to theta on this z. Okay, so let me omit the independent variables. Then you use your chain rule. So it must be what? Must be del z del x times del x del theta. Okay, then plus del z del y times del y del theta. Because you have only two variables, x and y, that depends on r and theta, right? So you can imagine when theta change, it's going to cause x to change. And then it's going to cause y to change. Then when x and y change, it's going to cause z to change. So you must sum up the two changes with respect to x and y. So then if you write this down, right, then you just differentiate accordingly. So this one, differentiate this. Okay, so del z, del x, you differentiate tangent inverse, it's going to give you 1 over, okay, 1 over 1 plus x squared over y squared, because it's x over y whole thing square. Then after that, you have to use your chain rule, because you have this tangent inverse x over y. So now you differentiate respect to x, so you get 1 over y. So let me just highlight this. So del z, del x, right, is just this expression. Okay, so of course I use the derivative of the tangent inverse. Okay, so let me write. So when you d dx of tangent inverse x, you're getting 1 over 1 plus x squared. Okay, so you can see, now I must 1 over 1 plus, because the argument is x over y, so it must be x over y whole thing square. Then because you have a function of x here, so you're going to use chain rule, differentiate x over y respect to x. So you get 1 over y. So then this del x, del theta, you can multiply. So del x, del theta is really just r sine theta, or rather minus r sine theta. So minus r sine theta. Can So then your del z, del y, you also do the same thing. You have to have 1 over, because tangent inverse ma. So 1 plus x over y whole thing square. Then after that, so now you have to differentiate x over y respect to y. So this is going to give you minus x over y square. Then the del y, del theta, you plug in, which is just r cosine theta. Is that okay? Can Yeah. So then this is not the complete answer, because you got x and y, and then you got r and theta inside the expression. But this one you want to get with respect to r, correct or not? So differentiating respect to r, by right, this whole thing, right, should be in terms of r and theta only. You shouldn't have the x and y. So therefore you need to sub in and then evaluate. Okay, but there's a simpler way to sub in. Because what is r sine theta? R sine theta is y, correct or not? Correct, this r sine theta is y. So that means I have minus 1 over y square here. So let me write, this r sine theta is actually y. Then this r cos theta is actually x, correct? So that means this expression simplifies to 1 over, sorry, it should be, let me see, minus 1. Minus 1 over, there's a y square here, but there's also a y square here, correct? So this is minus 1 over y square plus x square. Because the y square here, right, will divide off the y square at the denominator here. Then plus, then this one, right, will be, so you can see this x here will cancel the x here. So therefore you have minus 1 over y square. Then you multiply in. So therefore this is also a negative. Minus 1 over y square plus x square. Is that right? Correct? You can see minus 1, so it's minus 2. Minus 2 over y square plus x square. But y square plus x square is r square what? This is minus 2 over r square sine square theta plus r square cosine square theta. I mean you sub in. Then this is minus 2 over r square. Then you get sine square theta plus cosine square theta. So then this one is minus 2 over r square. Then this here. I mean you can always just come from here, right? Because y square plus x square, this guy is always r square. So if you want, you can like take the shortcut. Like this thing is r square. Okay, then you can come from here to here also can. Is this correct? Minus 2 over r square, is that the answer? Yeah, del z, del r. That means I made a mistake. Okay, I made a mistake because it should be 0. Where is the 0? So that means must be some plus minus thing. Huh? This one? This one? Okay, so it's like that. You see, this one is x squared over y squared, correct? Then if this is a y times y, oh yeah, you're right. This is not at the denominator. Okay, so I made a mistake. So this should be a 1 or minus 1. Okay, my fault. Hold on, so this part I made a mistake. Okay, so this one is minus y divided by y. Minus y divided by y. So therefore, this guy should be minus 1 over 1 plus x squared over y squared. You're absolutely right. Okay? Yeah, thanks. So this one is actually minus x. Then minus x. So it should be minus x squared over y squared, right? Okay, hold on, let me see. So this is 1 plus x squared over y squared. Then this guy will be multiplied by minus x squared, right? So I have, this is a plus. Then this guy will be minus x squared over y squared. Correct, huh? Okay? Yeah, so therefore, from here, right, because we have this minus x squared over y squared, so, let me see. No, I'm just thinking how to simplify it more nicely. Because it is r squared, what? So the r squared cancel, then you get the cosine over sine. So there's a minus here, right? It's a minus. Okay, so I'm going to have minus 1 over 1 plus x squared over y squared. Then this guy multiply by 1 plus, because there's a 1 here, right? 1 plus x squared over y squared. Is that right? Because there's a 1 here, I factorize out the minus 1. Okay, then the common factor is 1 over 1 plus x squared over y squared. Then if I multiply by 1, I get this term. Then I multiply by this term, I get the second term. Agree or not? Agree, Then I'm in trouble. I got minus 1. Is that a mistake? Is either my answer wrong or my working wrong? dz dr. Wait. You are looking at part C, is it? dz d theta is minus 1. Oh, no wonder I made a stupid mistake. So this should be z sub theta, not z sub r. Hey, my bad. This one is del theta. Okay, so this should be z bar sub theta. My bad. Okay? So indeed, this is minus 1 is correct. Okay, because I'm differentiating respect to theta here, not r. Because it's del theta ma. So this one, my fault. Okay, so this will be z bar sub theta instead. So indeed, this is minus 1. Okay? So we can do z sub r as well, of course. Is that alright? So this should be z bar sub theta. Can Okay? So we can also do our z bar sub r. So z bar sub r, right, no need to redo everything lah. Okay? Why? Cancel. This and this will cancel. The denominator here will cancel this one I can cancel with this one. Okay? Okay. So for z bar sub r, right, you don't need to redo everything. You just need to redo the part for the del x del r part. Okay, so you can see I just changed this one sub r, this one sub r, this one respect to r, this also respect to r. Okay, so then the pink part will change. This pink part will change, but the green and blue part no change. So this one sub r, then this one is del r, then this one is del r, then this one is del r. Can Okay. So therefore, what is your del x del r? Del x del r will be just cosine theta times cosine theta, because x is r cos theta ma. So differentiate respect to r will give me cosine theta, and then differentiating y respect to r will give me sine theta then. Is that right? So then from here we need to simplify. Okay? So once again I can, so there's a y here, right? Let me see. This cosine theta. Okay, so maybe I'll just sub everything in terms of r and theta into this expression. Okay, probably it makes it easier. But because I got x over y here, right? You see the x over y. So therefore, let me just work out at the side. So x over y is really r cos theta divided by r sine theta. So therefore, it is really just cosine theta divided by sine theta, right? So that is cotangent theta. Is that okay? Right? So that's cotangent theta. So I'm just going to sub in. So it's going to be 1 over 1 plus cotangent square theta. Then this 1 over y, right, will be just 1 over r sine theta. R sine theta. Then you have the cosine theta. So maybe I'll just put a cosine theta here. Then plus. Then the second term will give me 1 over 1 plus cotangent square theta as well. Then multiply by, so there's a minus here, so I shift the minus forward. Then this x over y square is going to be, sorry? Because y is r sine theta. I just sub in, okay? So then this part, right? So x will be what? R cos theta, then there's a sine theta here, times sine theta. Then divided by y square, which is r square sine square theta. Okay, so you can cancel off terms and you can see that they will cancel directly. Because this is a r, cancel. Then after that there's a square here, so cancel the square, become power 1. Then same thing goes for the sine. So the sine theta can cancel off the square here as well. So then what is this term? This term is actually cosine theta over r sine theta. It's the same as this term. So therefore it's 0. Because this one, right, eventually simplify to cos theta over r sine theta. Is that right? This is basically just, okay, to tell the truth, right, if you get a second step correct, okay, if you write until this part correct before the simplification stuff, right, actually you get quite a bit of marks already. Okay? Then the rest just sub in the x and the y and then try to simplify. So this one is the arithmetic lah. Okay, the first part is more important because first part cannot get wrong. Is that right? Okay. So this will be for question 6. Question 6C. Okay, so by right, this should be del instead of d because your z is a function of r theta. Alright. Okay, so maybe we take a break. Do you need a break? Maybe it's good time to take a break. 11:25. Any questions can look for me? Okay, so can I just leave the rest of question 6 to you? Any other requests for question 6? Can Okay, so question 7. Question 7, important. So I'm going to go through question 7. Then past year you try DIY, also using chain rule. Okay, so question 7 will be our last question for the tutorial today. Okay, why important? I also don't know. So this question is actually testing you on the understanding of the chain rule, okay? But without doing the differentiation. That means it's testing you kind of in the conceptual understanding of the chain rule, okay? So no differentiation needed, right? Okay, so the story is like that. Now you have this composite function, right, which is big F of x, y, and z lah, okay? And then because x is a function of s and t, y is a function of s, z is a function of 2 sine t, so therefore you sub in all the s and t expressions, eventually you are getting a net expression in ST. So this W, right, represents that net function in ST, the eventual function after you have simplified this expression, for example. So now you are supposed to identify what is W sub S, right, at 0, 0. Okay? So it goes like that, right? W sub S must be differentiating del S of this big F function. Agree, ah? Okay? So of course you need to use your chain rule here, right? Because F is a function of X, Y, and Z. So it goes to show that, so allow me to write shorthand here. So it must be F sub X, right? Times X sub S. So del F del X, because you can see that when S changes, it's going to affect X. So it's going to cause X to change. X change cause F to change. So that's accounted for by the first chain rule term here. Then, but because when S change, it's going to cause Y to change also what? Then Y change cause F to change. So therefore you have the second chain rule term, F sub Y times Y prime. Okay, Y prime, because Y is only a function of S. You can put Y sub S, no problem, it's also correct. Okay, Y sub S is also perfectly correct. You can put Y sub S if you want to. Okay, then you can look at this Z. So, but Z is not a function of S, what? So you can write like plus F sub Z times Z sub S. So that means you try to differentiate Z respect to S. But you realize that this Z sub S is equivalent to 0 since Z is not a function. Is not function of S. So therefore you have only the first two terms. Is that right? Okay, so this whole term is basically 0. The last term is 0. So this last term is 0. Can So let's evaluate the first two terms. Okay, and we now put in the coordinate. Let's put in the coordinate. Okay, so from here, right, you know that at 0, 0, W sub S at 0, 0. But what is the 0, 0? It's the S and T. This refers to S. This refers to T. So which means F sub X must be F sub X at 0, 0. Y at 0. Z at 2 sine 0. So 2 sine 0 also 0 lah. Okay, but just to write it completely. Okay, then it's going to multiply by X sub S at 0, 0. Okay, because X sub S, right, you can see the S and T here, right, also at 0, 0. Can So this is the first term. Then the second term. So F sub Y. So must be F sub Y at the same coordinates. Okay? Then you have your Y prime times Y prime. So Y prime is a function of S. So therefore this is 0. Okay? Because your S equals to 0, what? So Y prime at S equals to 0 lah. Then the last term, of course, is equivalent to 0. No need to write. So now then you need to look at this expression. So what is the X at 0, 0? The X at 0, 0, okay, let me write in blue. This guy. X at 0, 0 is 2. So that means this is F at 2, comma. So what is Y at 0? Y at 0 is 4. So this guy is 4. Then the Z, so 2 sine 0 is actually 0. This is 0. So Z at 0 is 1. Z at 0 is 1. You see, so it must be F sub X at 2, 4, 1. Any objection? You cannot use other coordinate. Let's say I give you 0, 0, 2. If you use this one, wrong. Is that okay? So it must be F sub X and F sub Y at 2, 4, 1 that you are supposed to use. Okay, so this F sub X at 2, 4, 1. Here, 6. So this is 6 multiplied by X sub S at 0, 0. This guy, X sub S at 0, 0 is where? X sub S at 0, 0. So it's this one. Minus 1. So it's minus 1. So it's a minus 1. Then you have a plus. Then F sub Y at 2, 4, 1 is this one. 0. F sub Y at 2, 4, 1 is 0. Okay. Then, of course, multiply by Y prime 0. So just for completeness with sub in is 1. Can So the answer is minus 6. Any objections? Okay, then what about the W sub T? W sub T. So W sub T is just del T on F. Okay? So obviously I no need to like rewrite this, right? I can just copy and paste. I choose all the sub S. I just change all the sub S to sub T will do. You see, so the sub T here. Sub T. Then this is Y sub T. But Y sub T is 0, right? Because Y is not a function of T. Equals to 0. Since Y is not a function of T. So therefore the second term will be 0. This whole term. So you have only 2 terms. Okay, the first and the third. Can Okay, so let's evaluate. Okay, so you look at this expression, right? Of course I can put in the coordinates, but I want to write one more step. So it's really the first term plus the last term, but I can evaluate the last term further. Now this last term, you have your F sub Z, but you see, this is Z sub T. Z with respect to T, differentiate Z respect to T. But what is your Z? Your Z is a function of 2 sine T, okay? So let me write Z equals to 2 sine T. Oh, sorry. Z as a function of 2 sine T. So you want Z sub T, right? So that means you are supposed to differentiate Z with respect to T. So d dt on this. But you can see that this is what? Function of T, what? So there's a composite function there. So which means you got to have Z prime, right? Correct or not? So what's Z prime? Z prime of 2 sine T times the chain rule, 2 cosine T. Is that right? Okay. So therefore, this is your Z sub T. So hence you plug the Z prime as a function of 2 sine T times 2 cosine T. Correct or not? This is actually your Z sub T. So this Z sub T is this guy. Is that right? So then now we can sub in the coordinates. Any questions with this or not? Okay, so W sub T at 0, 0. So it has to be F sub X at 2, 4, 1. Then X sub T at 0, 0. ST is 0, 0. So plus F sub Z at 2, 4, 1 as well. Then multiply by this expression. So this expression is going to be 2 Z prime at 0 times cosine. So T is 0. Okay, hold on, maybe I change this color so that it's clearer. Okay, so this part, right, is actually the black part. Any objections? So then you can just plug in the values ready. So F sub X at 2, 4, 1, we know is 6. This one just now obtained already. Then the X sub T at 0, 0. So look at the values. So X sub T at 0, 0 will be 3. So it's 6 times 3 plus. So F sub Z at 2, 4, 1 is 5. Then you must multiply by 2. Then you have a Z prime 0. So Z prime 0 is 8. Wait. I better write that. 2 times 8. This one is 8. Then cosine 0 is 1. Just to be complete. Okay? So then you calculate that. So therefore this looks like 18 plus 5 times 2, 10 times 8, 80. So the answer is 78, which is wrong, 98. Is that a given answer? Okay, so the W sub T part, W sub T part, you have to be careful because you have a Z that is a function of 2 sine T. So the composite function and usage of the chain rule will need to be applied when you differentiate Z with respect to T. Is that all right?
I understand like the working and everything. My question is, how do you even generate this first equation? Like
chain rule.
chain rule.
Just like question 6. The del thing. This is del f del x times del x del t plus del f del y times del y del t. Chain rule. I just write shorthand. Okay. So good. We are done with tutorial 6. So I think the last question, which is on the partial assessment, right? You can probably try it out on your own first. Okay? So if need be, we can go through during the next tutorial or the next lesson. Okay? Because I feel that this one quite straightforward. So it's 11:45. We still have some time, so maybe we can go through, continue the vectors part. I mean, we cover what we can. Okay, so first of all, I just want to mention that because yesterday I didn't draw the basis vectors U1 and U2 very accurately. Okay, so I think if you watched the recording or you came for lesson yesterday, right, I mentioned that this is like minus 1.5 U1 plus like 4 U2, or rather minus 4 U2, something like that. Okay, so you can see I draw this more accurately now, right? So if I define using the basis U1 and U2, right, so you can see that this is about like 0.7 U1 minus 0.7 U1. So I put minus 0.7 here, okay? Then after that, I can go in the reverse of the U2 direction for 5 steps. So it should be a minus 5 U2. Can okay? So nothing much. This is just trying to illustrate that you can identify any position in the 2D plane by using any two basis vectors that are non-parallel, okay? Okay? Yeah, so yesterday we finished off with the introduction on complex numbers, okay? So complex numbers, as you have observed, can be expressed as a point on the complex plane, right? So complex plane is very similar to XY plane. It's actually the XY plane. It's just that you let your X be the real number, you let your Y be the imaginary number, that's all, okay? So therefore, Z, right, which is a complex number, can be expressed in the complex plane. It's a point in the complex plane. So yesterday I have a very good question, and that is, right, I mean, why they invent these numbers for what? Okay, actually the truth is, right, the complex number is being used in the definition of complex functions. So it can be a function of a complex number Z, okay? So then this thing actually quite powerful because one of the very powerful applications is called the Laplace transform as well as the Fourier transform, which you will learn in Math 2 and 3 and also apply in many of your engineering modules. For example, you have a module called signals processing. So you process whatever signal, like a sound signal, right? A sound signal comes in. Then you want to extract, for example, the low frequencies, and you want to discard the high frequencies. Let's say you want to do like a sound processing whereby all the high pitch noises, right, gets eliminated, gets filtered away. So in order to extract all the low frequencies from the sound signal, you need to be able to transform into a frequency function. So that frequency function comes from what we call the Fourier transform. Okay, so you have like, let's say for example, I am speaking now. Then for some reason, right, there is a high-pitched background noise in my speaking, maybe due to the feedback from the microphone. Okay, the microphone not fantastic. So therefore, how do I filter away the high-pitched, irritating frequencies? So I have the sound signal is a function of time. I feed into the Fourier transform. After I feed into the Fourier transform, it gives me a function of frequency. Then I can just decide a cutoff. Let all the frequencies above this cutoff frequency be 0. Meaning to say, let all the amplitude be 0. Okay? So therefore, I can reconstruct the sound signal back, and therefore, I have my improved sound quality, for example. So that Fourier transform is a function, depends on this function of complex numbers. Okay, so this one you will understand more in your Math 3 as well as in your signals processing module. Okay, long way to go. Okay, so today left with 10 minutes. So I just want to finish up the dot product. So what's the deal with the dot product? Okay, dot product is an operation. It's an operation between two vectors. Let's say, for example, u and v. So just look at the diagram here. Okay, guys. Okay, obviously this long vector here or longer vector here is the vector u. Okay, so I of course write this as the magnitude. I'm referring to the magnitude here, but this is obviously vector u. And the red vector, right, is vector v. So what's the dot product? Okay, dot product is just defined as the magnitude of u times the magnitude of v cosine theta. Very simple. Okay, so I just take the lengths of u and the length of v, right, multiply together, and then I have a cosine theta here. Okay, can you see cosine theta? But what is actually the graphical understanding or the geometrical understanding? Now it's very easy. Now you see, you can say that the cosine theta belongs to u, correct or not? So if the cosine theta belongs to u, then you have u cosine theta, right? But u cosine theta is the projection of u onto the direction of v, what? Because u cosine theta is giving you this dotted green arrow. Is that right? Because theta is the angle between the two vectors. So therefore, u cosine theta must be giving you this green dotted arrow. So that means you are taking the projection of u onto v, then multiply by the length of v. Okay, so if you treat this cosine theta to be part of u, is that right? So let me write. The first one is like u dot v must be equivalent to u cosine theta times v, times the length of v. Okay, so the u cosine theta here is the projection of u on v. So this one, you see, projection of u. Projection of u on v. Is that right? But you can also view it in another way. And that is right, this cosine theta belongs to v. This cosine theta belongs to v. So you can see that I can also project this v, red v, onto u. So I get a v cosine theta. Can you see? So I take v cosine theta, which is the projection here, multiply by the length of u itself. So therefore, this is another perspective. Okay, just another perspective, right, of how you can view the dot product. But dot product is just magnitude of u, magnitude of v times cosine theta. Simple as that. Is that alright? Can, Okay. So basically, this is just, the dot product is just taking the projection of one vector onto the other and multiply by that vector itself. Okay, so let's look at this exercise, and then really I want to give you a layman description of the dot product. Okay, because dot product, it looks like a vector operation, but actually there's a layman understanding. Okay, so first of all, let us write down the dot product values here. Okay, so once again, u dot v is length of u times length of v cosine theta. So we can just plug in the values here. So what is this value? Now obviously it's just length of u times length of v, because cosine theta is 1 what? Cosine 0 is 1. So this part, right, cosine 0 is 1. Minus 1, so it has to be minus of the lengths multiplied together. Okay, so what about if it's 0 to pi over 2? It must be 0 to length of u times length of v, correct or not? So that means this dot product will be positive. Okay, it will be a positive value, positive dot product. Then if the angle is obtuse from pi over 2 to pi, then the dot product will be negative. Is that alright? Let's say this can be your v, this can be your u. Is that alright? So this means that the vectors u and v themselves are perpendicular. Okay? So what is the layman characteristic or layman description, right, of the dot product? Now actually, if you look at the dot product, it's trying to compute how similar or how two vectors are pointing in a similar direction. Correct or not? Because if the two vectors, right, they are pointing in exactly the same dimension or the same direction. Okay, if the two vectors are pointing in exactly the same direction, then you have a maximum dot product, you know. Isn't this a maximum? Because cosine theta is always 1 or less than 1, ma. Correct or not? It ranges between -1 to 1. So the maximum of this, right, is actually the upper bound. This one is within the interval from minus u times v to positive perpendicular, right? Which means pointing in totally different direction.